Welcome viewers. I am Venkatesan. Today my lecture is about principle of strong induction and well ordering. Principle of strong induction, that is second principle of mathematical induction. To prove a propositional function p of n is true for all positive integers n, we have to compute two steps. I hope every one of you has remembered what are the two steps that we studied in mathematical induction, that is basis step and inductive step. Here also we are going to continue the same two step with small changes. First one, the basis step is which is quite similar to your mathematical induction only. That is, we are going to verify that P of 1 is true. But in inductive step, in mathematical induction, we assumed P of k is true and we was trying to prove P of k plus 1 is true. But in principle of strong induction, while inductive step, our assumption is P of n is true for all integers which lies between 1 and k. Remember, in mathematical induction, we considered directly P of k as true. But here we are considering all integers which lies between 1 and k is true, and we are going to prove the same P of k plus 1 is true here. Next, well ordering property. The well ordering property states that every non-empty set of non-negative integers has a least element. For example, if you consider a non-empty set like 1, 2, 3, 4, 5, which means that what is the least element in that set? 1. So, whenever you consider a non-empty set of non-negative integers, it must have a least element. That is well ordering property. If the proposition, you consider the note, if the proposition depends on one more than one basis condition or initial condition, we use the strong principle of induction. Let us discuss the problem. Question number 1. Prove that a positive integer greater than 1 is either a prime number or it can be written as product of prime numbers using principle of strong induction. Actually, this statement will be otherwise called as the fundamental theorem of arithmetic. That is what we want to prove. Every positive integer n greater than or equal to 2 is either a prime or a product of primes. For example, you consider 2 is a even prime number. 3 is a prime number. If you consider 4 is a composite number, means that will be rewritten as product of 2 into 2. I mean that product of prime numbers. That we are going to prove now. Solution. Let the proposition be P of n such that every integer n greater than or equal to 2 is either a prime or a product of prime. First, let us discuss the basis step. What is the initial value here? Since n greater than or equal to 2, we want to verify that P of 2 is true. That is, when you consider P of 2, we are getting 2, which is directly a prime number. No need to consider the product of prime here because already 2 is a prime number. Next, in inductive step, as I said, we are going to assume the integers which lies between, I mean up to k, all the values are true, that we are going to assume, so that P of 3, P of 4, P of 5, etc. up to P of k is true. Next, we want to prove P of k plus 1 is true. That is, to prove k plus 1 is either a prime number or product of prime number. So we have two different cases now. In case 1, if k plus 1 is prime number, means that is a trivial case. No need to prove anything. We get the result directly. If k plus 1 is not a prime number, if it is not a prime number, means it should be a composite number. You consider any one composite number. Let me consider the composite number as 6. How can we rewrite this 6? That 6 will be rewritten as product of two prime numbers, that is 2 into 3. Remember, the 2 and 3 lies between that 1 and k plus 1. Accordingly, here, since I considered k plus 1 is not prime, that is the composite number, it can be written as product of two integers, that is x comma y, where that x comma y lies between 1 and k plus 1, which means that x plus 1 will be rewritten as x into y. Hence, P of k plus 1 is true. Therefore, by principle of strong induction, P of n is true for all n greater than or equal to 2. Thank you.